All right, it's 4 o'clock. Let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? You're good? All right. So today we're going to be just continuing our discussion of nonlinear programming methods. Okay. So I did just post the new homework. So homework 5 is posted online. So this is going to be the most code intensive problem set that we're going to have. Because with the exception of problem 1, every single problem in homework 5 is going to involve code writing. So and so some of the codes are going to be as simple as just kind of taking the example codes that we've done in class and just kind of swapping out the objective function, maybe swapping out the bounds for the design variables. So some of them are going to be pretty straightforward. But I did include a couple problems on the homework where you do have to kind of combine some codes together and write a little bit of your own code as well. Okay, so there's kind of a good mix of kind of easy codes to medium codes to kind of more difficult codes. Okay, and this homework is going to be really important for us. First of all, we do have the second midterm coming up, I think, right before Thanksgiving. So maybe like 2.5 weeks. But it's going to be especially important for your final project, where your final project, you're going to be expected to write code that's very similar or very much like what's in homework 5. Okay? So homework 5 is I think probably the most important code that we have this class so far. And one thing that I did, so I am going over all these example codes in the class. All of those are available to you online. But one thing I'm also doing for this homework is that I'm also linking the codes, the example codes that are particularly relevant in the assignment itself, right? And then within the assignment, I've kind of labeled each of the problems to kind of tell you, or to give you kind of very heavy hints in terms of, which example codes kind of correspond to each problem. Okay. So definitely check that out. Definitely look at that. It's going to be due in about 2 weeks. So you're going to have 2 weeks to do homework 5. Okay. All right. So speaking of the project, I did tell you guys that we were going to talk about it this week. I decided because homework 5, I wanted to make sure to get that out to you today. Let's talk about the final project on Thursday. Okay. But just to kind of give you a little bit of a heads up, the final project is going to be an individual project, so everyone's going to do their own. So we're not going to have to worry about forming groups or anything. But it's basically going to be the same as homework 5, except with more difficult optimization problems. Okay. And basically what you're going to do is that once you have the project, it's going to be a more difficult optimization problem, and it's going to be up to you to choose which algorithms would work the best on those problems. Okay. All right, and so that's all my announcements. Are there any questions on anything before we get started for today? Okay. All right, so let's go ahead and get started. And so I think where we left off last Thursday was we were talking about random walk method. So let me actually go back to that. Okay. So this all just kind of repeat from last time, so you don't have to write any of this down. Okay. But basically the idea with random walk is we want to improve on our random jumping or Monte Carlo methods. Okay. And kind of one of the biggest weaknesses of the Monte Carlo method was that, because we're jumping around just kind of everywhere within the problem domain, everywhere within our viable region, if we do find a spot that's particularly good, we kind of jump away from it before we kind of explore that further. Okay. Because the thing with a lot of these optimization problems is that generally speaking, the optimum is in kind of one place. And once you kind of start getting warmer, you want to start kind of searching around that area so that you can kind of, improve that guess. Okay. So where Monte Carlo methods are really good at kind of doing a kind of a broad exploration of the entire domain, sometimes you might miss a lot of details. You may reject a lot of points just because you don't really have any kind of sense of memory. That's kind of the term that we use in this field. Okay. So random walk hopes to kind of rectify this, where whenever you're choosing new design points to test, instead of kind of just jumping around randomly within the viable region, you're going to just search just kind of one step away from your current point. Okay. And the direction and the length of that step is going to be somewhat random, hence the name random walk. Okay. Okay, and so the way it works is that we're going to start with an initial guess, with some value. So we call that x naught vector. Okay, And we also need to define our all of our parameters. So the step length, the minimum allowable step length, the number of iterations per cycle. Okay, so we'll go over what all those mean in a second. Okay. And so, I'm just, so this is all just review from last Thursday, but I did want to go through each of the steps of this algorithm so that we can kind of just look at the code and see how each of these steps are implemented in the code. Okay. And generally speaking, whenever we go over algorithms in this class, this is kind of the style that we're going to go with. So we'll kind of describe the algorithm or the steps of the algorithm using words, kind of in a traditional kind of lecture format like this. Okay. And then what we'll do after that is we'll go over the example code and we'll see kind of how each step in the algorithm is implemented in the code. Okay. So definitely write this down. And then, as we're going through the example code, you should be able to see how each of these steps are implemented. Okay. Okay, so step 2 is to evaluate the objective function at the initial point. Okay, and so whenever we have an optimization problem, we're always given our objective function, right? And so if we have our initial design point, we can plug that into our objective function and get our initial function evaluation f naught. Okay. Okay, and then from there, starting with step 3, this is when we start going into the walk part of the algorithm. So we need to generate kind of one important thing, which is the direction. Okay, so we need to find out kind of what direction we're walking in, and so we need to generate this vector ui, which I'm calling the step vector. Okay, and so the way the step vector works is that we're generating a random number for each design variable that we have. Okay, and so let's say that we have 3 design variables, right? So our step vector here is going to be a vector of length 3. Okay, where each entry in that step vector is, corresponds to that variable. Okay. Okay, so the direction that we choose here is going to be really important because first of all it's going to be random, but we do have to kind of place a little bit of constraints on it just to make sure things don't just kind of don't really get out of control. And so we impose this requirement right here where if we take the norm of the direction vector, we basically take its magnitude. If this is greater than 1, then we actually reject this this direction just kind of right away, right? And this is important because if that magnitude is greater than 1, then we're going to start to bias our direction. So we're going to start walking towards the corners of a viable domain where we kind of want to make it a bit more balanced with that. Okay. Okay, so once we have the step direction, we're going to add that to our current point, and so we apply this formula right here. Okay, where x sub t being our new guess, is going to be equal to our old guess, x sub I, plus lambda, which is our step length, plus our direction vector ui, which we just determined in the previous step. Okay, and so hence the name of the algorithm as random walk, right? So our new point is we start from our old point and then we just take one step in a given direction from that old point. Okay. And then once we arrive at that point, we're going to evaluate the objective function at that point. So we call that f sub. Okay. Okay, and then step 5 here. Step 5 is the most important one. So step 5, we check to see if this is an improvement from our previous location. Okay. And so even though we're taking steps in kind of random directions in its algorithm, we want to make sure that the steps that we're taking actually lead to an improvement of the objective function. Okay. And so we have a check. And so you're going to see this as an if statement in the code. Okay. And so if the previous step led to an improvement of the objective function, and so we find one that's more negative or less than the previous step, then we accept it, and we actually step there. If not, then we reject it and we return to our previous location. Okay. And then we're just going to repeat steps 3 through 5, multiple times, right? Until we reach our max iteration counter. Okay. Okay. And then from there, we're going to repeat that entire process again because kind of the logic here is that as we take steps, we're going to get closer and closer and closer to the optimum. At least that's the hope, right? And so as we get closer and closer to the optimum, we should reduce our step size to kind of make sure that we're not overshooting the optimum, or we're not kind of, taking too big of steps. And so we're going to reduce the step size, and then we're going to go back to step 3. Okay. And then we're going to repeat this until our step size kind of gets down too low. Okay. Okay. And so let me kind of draw this kind of visually, because it's kind of one thing to kind of read an algorithm like this and kind of read the steps. I think it's always really helpful to kind of visualize what's going on. Okay. Okay. Let me go ahead and draw a 2D domain. Okay. So you're going to see me use 2D problems as kind of illustrations for these algorithms, just because 2D is the easiest to draw. Okay. And so let's say that our optimum is somewhere over here. Okay. Right. Where the horizontal axis here, that is going to be the value of our first design variable x1. And the vertical axis here is the value of our second design variable x2. Okay. So let's say that we start our random walk from right here. Okay. And so eventually we want to be able to move to where the optimum is. Okay? Granted, before you start any optimization problem, you don't know where the optimum is beforehand. Okay. So we're kind of cheating a little bit here just to visualize it. But let's assume that we know that the optimum is in that location. Okay. So we want to move in that direction. And as we get warmer and warmer to the optimum, what we should observe is that the objective function should get less and less. And so that's going to lead to an improvement. Okay. Okay. So we start there. And then from here, we're going to generate a random direction. Okay? So let's say that we generate a direction in this one right here. Okay? So this can be U1. Okay. All right. So if we look at this direction U1 relative to where we started, we're getting closer to the optimum, right? So if we were to kind of take a step in this direction, this is going to lead us closer to the optimum, right? And so, this arrow I just kind of drew randomly, right? And so we could have very easily kind of stepped in another direction, okay? If RNG was not in our favor, but in this case, RNG was in our favor, okay? And so we step in that direction, we check the objective function at our new location. We find that it's an improvement, right? Because we're getting closer to the optimum. And so this is a point that we would accept. Okay. So that's a step in the right direction. So we were kind of lucky in this case that we kind of randomly chose a direction that led to an improvement. And so we were able to kind of improve our objective function. Okay. Okay. So that's the first iteration. So that's good. So let's take another step. So let's from this new location here, let's say that our random number generator generated a direction that's like I don't know, like this. Okay. And so we start kind of heading downwards, kind of towards the bottom of the domain, right? And so relative to our previous location, this direction here gets us actually away from the optimum, right? And so that should hopefully be expressed once we evaluate the objective function at both of these locations. So at our original starting location and our new one here, okay? And so this would be an example where we would reject this step, because this stepping in this direction would not lead to an improvement of the objective function. Okay? So we're going to reject that, and we're going to stay where we were before, right? So we're going to stay at that second dot right there. Okay. Okay, so from here we say, okay, that direction didn't work. Let's generate another random direction. Okay. And so we run our code again, we're in the next iteration of the loop. And so say that we, generate a direction that's kind of more like this. Okay. Okay, so at least we're heading upwards, but the arrow kind of has a left leaning direction. Right? So a direction like this would be a toss up. So it's a little bit hard to tell in this case, just because we have one location of an optimum, if this is actually getting us warmer or not. Okay, but just for the sake of argument, let's say that it does get us warmer. Okay, and so if that location there led to an improvement of the objective function, we can accept it and then move to that point. Okay. Okay, and then this is just going to continue on and on. So, we're going to test a direction. Okay, if that direction doesn't lead to an improvement, we're going to reject it. Okay, then we test another direction. So let's say that we move in this direction here. Right, that's an improvement, so we can stay there. Okay, we test again. Maybe go like that. That's not an improvement, so we reject that one. Test another direction. That is also not an improvement, so let's reject that one. Okay. Maybe we test this direction here. Also not improvement, so let's go ahead and reject that. Okay. Sometimes you're going to go through many, many rejections per cycle, and that's totally fine. Okay. And sometimes it kind of takes a while for you to generate the right direction because it's all random, right? And so you don't really have a lot of control over it. Okay. So let's say that we go there. Maybe this time we get lucky. We get to move there. Okay. Right, because that's generally still in the right direction. Okay, and so you can see we're kind of taking like almost like a haphazard kind of approach to the option. Okay, or it's random, right? So we're generally stepping in random directions, but by checking to see if the objective function improves, over time, eventually we should get closer to that option. Okay. All right. Any questions on this so far? Okay. Okay, so let's pause here. And so now that we've kind of reached this point here, we're getting closer and closer to the option, right? And so what the algorithm says that, as we get closer and closer, we should make our step size smaller. And so, I didn't do a very good job of this, but, we're going to assume that every step that we've taken so far has been the same length, okay? But from here on out, because we're getting closer, let's go ahead and take smaller steps. So we're going to reduce our step size so that we don't overshoot the outcome. Okay. Because what can happen is, so let's say that we're right here, right? I'm just kind of skipping ahead a little bit, right? So let's say that we're right there, but our step size is too big, and so let's say that we step in the right direction of the optimum, but maybe we just overshoot it like crazy because our step size is too big. Okay. And so we may look at that point right there and be like, oh, that's, we're actually further away from the optimum than we were before, right? And so if that were the case, we would reject this. But that direction is actually really good because that direction is in the right direction of the optimum. We just need to make our step size small. Okay. And so what you're going to see in the algorithm is that, as the algorithm kind of runs more and more, the step size is going to get reduced. Okay. Okay. And so this can continue. Maybe we have a couple more rejections along the way. And if our step size is kind of sufficiently small, once we get closer, hopefully we arrive at the optimum or at least kind of right really, really close to it. Okay. All right, so that's kind of a visual representation of how the random walk algorithm is going to work. Okay, this is kind of an ideal case because if I drew more rejections, it would kind of get messy. But in reality, when you're running this algorithm, and when you're running Monte Carlo as well, there's going to be a lot of rejections, and that's totally normal. Okay. In fact, I ran a test code for your final project using Monte Carlo. I think somewhere around the lines of 99.9% of the points that we generated were actually rejected because they don't lead to an improvement of the objective function. So, and so if you have a very high rejection rate, that's completely normal. In fact, that's kind of the expectation. Okay, any questions on this process here before we start to look at the code? Okay, all right. So keep that process in mind. Keep that algorithm in mind. And so as we look at the code, you're going to start to see the different steps of the algorithm and how they're actually implemented in the code. Okay, so let me go ahead and share my computer screen here. Okay, and so this code is on Canvas, and so this is the code. Let me see what it's called. So this code is called UNLP example 2 random walk. Okay, so this is our second code example for nonlinear programming. Okay, so hopefully you have your notes in front of you in terms of the steps of the algorithm, and let's go through each of the steps of the algorithm and see how they correspond to the code. Okay. Oh, I didn't even write down the example problem for you. So the example problem that we're trying to minimize here is we have this function right here. Okay, so this is a two-dimensional function. So we have two design variables. We call them x1 and x2. Okay. Yeah, we'll just read it off here. Okay, and so our objective function is x1 minus x2 plus x1 squared plus 2x1 x2 plus x2 squared. Okay, so that's our objective function, and we want to find the minimum of this objective function. And in this case, we're going to use random walk. Okay, I think before we use Monte Carlo for this one. Okay, so let's go to step 1. So step 1 is to establish our initial guess. And so our initial guess in this case is going to be 0, 0, right? And so if you look at the line 6 here, okay, and so in line 6, we're defining our initial guess. So we're calling our initial guess x1 underscore 0 and x2 underscore 0. Okay, so you can see we're setting both of those variables equal to 0.0. Okay, and so that is our initial guess. We have to set n. So big N is the number of cycles, number of iterations per cycle. Okay, so that is 500 in this case. Generally, the higher you set n, the more expensive your random walk is going to be in terms of the time it takes to run. But you're more likely to find the optimum in that case. Okay. Okay, we also have to set the step length, and so this is going to be the initial step length, which is 1.0. Okay. And then we have our minimum step here, which is the smallest amount that we're going to step, which is 0.05. Okay. Okay. So that is the step 1 of the algorithm. Okay. Step 2 is to evaluate our objective function at the initial point. Okay. So that is done here on line 7. Okay. And so what you can see here in line 7, we have our objective function, and we're plugging in our initial guess, right? So x1 underscore 0 and x2 underscore 0, okay? So we're plugging that into the objective function on this line right here, okay? And what that's going to give us is that it's going to give us a result f0, okay? Which is the initial objective function value. Okay. All right, and so before we actually start taking random steps, we have to kind of keep track of what is our current best point, okay? And so the current best point is going to be the point with the lowest value of the objective function, okay? So you can see here I'm creating 3 new variables. I'm calling it x1 best, x2 best, and so that's going to be the values of x1 and x2 at our optimum point, and f best, which is the objective function value at that point, okay? And so we only have one point so far. We just have our initial point. And so we're going to set these to our initial point and the initial value of the objective function f0. Okay. Okay. So from here we go into our walking loop, and you can see it's not that long of a code. So it's from here it's only about 30 lines of code. Okay. Okay. So the first thing we have here is a while loop. Okay. So while loops, again, are quite common in optimization. And so we have while step length is greater than minimum step, right? And so we remember we want to keep taking random steps until our step length is reduced below the minimum step length. Okay? So throughout this algorithm, we're going to reduce the value of step length, exactly kind of how we did in the picture. Okay, right. And then inside here, we start to actually generate random random directions. Okay. Okay. So first, I want to kind of draw your attention to line 25 and 26. Okay. And so in line 25, 26 here, we're using the the rand function within MATLAB to generate a random variable between -1 and 1. Okay. And so since this is a two-dimensional function, we need to generate two random variables, one for x1 and one for x2. Okay. So we're calling that R1, R2. Okay. And so the next line we're going to look at is line 29. And so line 29, where you can see we're computing the norm or the magnitude of the direction vector, right? So we're taking square root of R1 squared plus R2 squared, right? And so if that magnitude is less than or equal to 1, and so in other words, if our magnitude is small enough so that we're not biasing, then we can actually take a step in that direction. Okay. Okay, and so to take a step in that direction, we're going to use the R1, R2 vector. And so what we're going to say is that x1 trial, x2 trial, so we're defining two new variables here. X1 trial and x2 trial are going to be the trial values for x1 and x2 in this in this equation. Okay, so x1 trial here is going to be x1 best plus the step length. So step length, remember, is alpha times R1 divided by R magnitude. Okay. So this value right here, this is the kind of the normalized step direction. And so we take our step direction R1 and we divide it by the magnitude of its vector. Okay. And so we're going to do the same thing for x2. So x2, we're going to be taking our previous point and we're going to take a step. Okay. Okay, and so the next step here is that we're going to evaluate our objective function. And so you can see here that we have our objective function once again. And we're calling this variable f trial because right now we don't know. We don't know if this f trial is going to be an improvement over our previous point or if it's going to be worse. Okay. And so that's why we're calling it just a trial, because we haven't decided if we want to step in this direction just yet. Okay. Okay, and so here we're going to check. And so if f trial is less than f best, okay, and so if this condition is true, our trial point is better than our original. Okay. All right, and so if this is true, then stepping in this direction does lead to an improvement. Then what we're going to do is we're going to save our variables here. So we're going to say x1 best is equal to x1 trial, x2 best is equal to x2 trial. Okay, and so what these two lines of code here do, lines 39 and 40, this basically executes our step in the random direction. Okay. So we're saving the values for x1, x2 to be what their updated ones are from trial. Okay. And then from there, we then kind of save the value of the objective function at this location. Okay. And then we go from there. Okay. And so since this part of the code here is within a for loop, okay, this code is going to continue to repeat. So we're going to take steps, with this particular step length, with our random variable, but we're only going to accept the steps if it leads to an improvement. Okay. Okay, so this is kind of the code version of kind of what we just went over, both in words and both visually as well. Okay. And so even though I'm saying this is only like a 30, 40 line code, if you've never seen one of these codes like this before, it's going to take a little bit of time to go through. So, definitely make sure that, as you're working on the homeworks, you go through the example codes and kind of check and see, just to make sure that, you're kind of understanding how the algorithm works relative to the code. Okay. And I think honestly, I think that's the part where I think most people are going to struggle with, is that, I think the algorithms themselves, the logic for them is we can kind of talk about it and it makes sense. But then translating that logic and that set of instructions into code that a computer can read, I think that's kind of the hard part, because we, as humans, we kind of have our way of kind of describing things and explaining things. When you write code, you're basically writing instructions for the computer to do the same thing. And so kind of speaking that language just kind of takes a lot of practice. And so, if you're, if you're not confident, or if you're not kind of experienced with kind of this kind of train of thought of taking kind of logical algorithms and converting them to code, definitely talk to me, and I'm definitely happy to help you through that. But besides that, definitely check out the examples and kind of almost read them kind of side by side with the algorithms in the notes, so that you kind of get some practice in terms of this piece of logic becomes this piece of code, right? And so that's that's going to be an important skill moving forward. Okay. And so we're just about done. And so once we kind of loop several times, right? And so remember, the way this algorithm works, we're going to repeat steps a fixed amount of times. And so that's going to be given by n. Okay. After that, we're going to reduce the step length. And so we're going to say our step length is equal to step length divided by 2. Okay. So this is a fairly aggressive walk, because, we're having the step length in each iteration, which is fairly aggressive. Usually what you'll see is that if you're doing random walk, the step length is reduced by maybe about 20%, 10 or 20% per iteration. And with that, that's the end. Okay, so let me go ahead and run this so you can kind of see what it's like. Okay. Okay, so running this code here, what we get is, let me look for x1 best. So x1 best here is about -1, and x2 best here is about 1.5. Okay. Oops. And so if you remember from our Monte Carlo example, these were the exact values of the optimal parameters. So, using a random walk algorithm, we're able to get the same parameters or same optimal values, but with a lot less work, because we're walking instead of hopping around kind of all over the place. Okay, any questions on this? Yes. Exactly, right. And so if the optimization problem was maximization, then you're instead looking for parts or locations where the objective function is greater than the previous point. And so you would change yeah, right here. So this line right here. So you change this to a greater than. Yeah. Yeah, good observation. All right, any other questions on this code right here? Okay. All right, and so that's two codes that we've gone over now. So we've gone over the Monte Carlo code, and we've gone over the random walk codes. And so I consider these two to be kind of the two most, I would say, beginner-friendly codes. Okay. So you can see here that we're going to go through a lot of other codes. So actually, I don't have it up, but we're going to go through a lot of other codes in in this class, starting with another one today. And so when you're first starting out, when you're first doing homework 5, start with the random codes. Start with example 1, example 2, because that's kind of the starting point for taking optimization algorithms and putting them into code. And the codes themselves are fairly short, so they should be fairly easy to understand. So definitely do those codes. Okay. Okay, so let me go ahead and bring back. Let's bring back the iPad. Okay, so I was actually on week 10. So let me come back to week 11 here. Okay. Okay. So our next algorithm is called coordinate search, and so it kind of takes some inspiration from random walks, but it takes the randomness out of it. So it's a little bit more consistent. But actually, ironically, because it takes the random part out, it also kind of struggles in some ways too. So optimization is very interesting. So sometimes randomness is actually a good thing, because if you kind of stick to a given recipe every single time, some algorithms are not going to work for every optimization problem, because all the objective functions are very different. And so if you stick to kind of a preset algorithm, sometimes you're just going to make the same mistake. So some randomness is actually good in optimization, because it can kind of get you out of some situations that are hard to trouble otherwise. But before we get to coordinate search, I did want to make a few final comments on random search, random walk. Okay. So the first comment is actually the one that I just said. So maybe I should have written it down as I was saying. So sometimes because what can happen, and I think someone made a comment about this on Thursday, which is very astute, is that sometimes when you're doing an algorithm, you may get stuck in a local minimum. Okay. Let me kind of draw this visually so we can see again. Oh, excuse me. Okay, so same as before. We'll say our optimum is kind of in that upper right portion right there. Okay. All right, and so let's say, excuse me. Sorry, all the wind recently has kind of kicked up my allergies. Okay, so let's say that red dot is kind of where we want to go. Okay, but along the way, let's say that there are kind of a lot of smaller dots, or these smaller dots are kind of local minimum, right? And so, it may, when you're kind of in that vicinity, it may seem like you're finding the optimal value, but it's not as optimal as where the red dot is. Okay. So these blue dots here are local minimum. Where this red dot is the global minimum. Okay. Okay. So let's say that you're running a walk algorithm, like this, okay? And you're progressing, but then you kind of get stuck in this local minimum, right? And so think about how a random walk works. And so we're at this point right here. We're checking directions here, so we're checking all these points, right? Okay. You may have a situation where all those points that you check there are less optimal than our current one, right? And so if that's the case, and so if you're checking all these points here and you're finding points that are worse, you may be led to believe that this point right here is a maximum, or this is a minimum here. Okay. And then the way we say that is that your algorithm can get stuck. All right, one way to break this is to literally do something random. Okay. And so it's actually very surprising. And so if you look at kind of very high level kind of optimization codes, you may see parts of the code where the code will kind of intentionally make a bad step, right? And so let's say that we check a point here, right? And this point actually has a worse objective function value than our previous point. And so normally, we wouldn't want to go here because it's what we're observing is that it leads to not an improvement of our previous value. But sometimes you may need this, right? Sometimes you need to kind of break out of a local minimum. And so kind of more complex optimization algorithms, what they say that, if you're kind of stuck in the same point, for a long period of time, so let's say that you've tried in a lot of different directions, it may try to break out of this by, literally doing something random, either taking a big step in a random direction, or maybe just use a straight up Monte Carlo. So it said, we're stuck here, let's make a random jump. So let's jump over to this location here, and then start walking from there. Okay. And so it's very fast because and I would say in almost virtually every other engineering discipline, every other engineering class that you're taking, randomness is generally a bad thing, right? So doing random stuff is not going to be a productive way to approach an engineering problem. But in optimization, doing random stuff actually can help sometimes. Okay. And so random walk is actually susceptible to getting stuck, but because of its randomness, it can kind of just randomly break out. But actually, the best thing to do when you're stuck is to do just straight up Monte Carlo and just kind of jump wherever you can. Okay. So that's one good thing. That's one good thing about randomness. And so maybe a lot of other algorithms that you might see may not be pure random like these ones, but it's going to incorporate some randomness to kind of help with some of these problems. Okay, 2. And so the second point here is kind of more of a difference between Monte Carlo and random walk. Okay. And so I've kind of alluded to this a couple of times, but I think it'd be good to kind of write it down and formalize it. Okay. So Monte Carlo, just randomly just jumps everywhere in the domain, right? And so another name we call this was random jump. Okay. Monte Carlo is great when you when you want to search kind of everywhere in the domain equal. Okay. And so the terminology that I use for that is it's good for broad searching. It kind of just jumps randomly everywhere, and so you get a good sampling of kind of everywhere within your problem. Okay. Random walk, on the other hand, okay, because random walk has this kind of causal nature to it, and so just wherever you step depends on your current point, right? Random walk is much better suited for kind of improving, kind of almost like fine tuning a design point. Okay? But because of that, random walk is susceptible to getting stuck, kind of just as we previously mentioned. Okay? For Monte Carlo, it's impossible to get stuck because it doesn't, your next guess doesn't depend on your previous guess at all. Okay. And so these are kind of two separate kind of advantages. And so, Monte Carlo may be great at first. Maybe you use Monte Carlo at first to kind of, get an approximate location of where the global minimum is. And then you run random walk to kind of improve on that guess. Okay. And so kind of what I'm getting at here is that you can kind of combine these into one. You can combine both of their strengths together. So maybe you have a given optimization problem. Maybe you start with the Monte Carlo method where you just randomly guess everywhere, and then you just whatever you find to be the best one there. From there, then you initiate a random walk. Okay, and so you kind of get the best of both worlds in that situation. Okay, and so in fact, this combined code right here, this is going to be I gave this to you as a homework problem. So this is going to be problem 2C. Okay. Homework 5, problem 2C. Okay. All right, and so in that code, that's probably going to be the first. I would kind of rate that kind of a harder code compared to the previous, all the previous ones, because you're actually going to be, not just kind of bugging and chugging into it's an example code. You're actually going to need to kind of combine codes together. So you're going to take aspects of your Monte Carlo code, take aspects of your random walk code, combine them together, and then that's going to be problem 2C. Okay. So it's an interesting one, and this is I gave this to you kind of for the reason that combining multiple algorithms together is also something that's common in optimization, and in fact is something that I encourage you to do for your final project as well. Okay, which we'll talk about more on Thursday. Okay, and so as we're going through all the different algorithms, it's always good to keep in mind what are some situations where this algorithm is good at, and what are some situations where this algorithm is not good at. Okay, because a lot of times you can combine the strengths of multiple algorithms together to kind of make a better algorithm from there. Okay. Okay. So that's everything with the random method. So from here, we're going to do a lot less randomness. Any questions on any of this? Okay. All right. So let's go ahead and move on to the next algorithm, which is coordinate search. Okay. Okay, so the idea behind coordinate search is it's quite similar to random walk, where we're going to start from an initial point and we're going to take steps from there. Okay, but instead of choosing our step direction randomly, the way the coordinate search algorithm works is that instead of searching kind of randomly, we're only going to change one design variable at a time. Okay. But instead of a random direction. Okay. And so we take a lot of the randomness out of it. And so this algorithm is a lot more consistent. And so the interesting thing is that when you run your random walk and random Monte Carlo methods, you run the exact same code multiple times. Sometimes you'll get a different answer because of the randomness involved. But with these kind of more deterministic algorithms, assuming that your objective function is the same, if you run the same code over and over again, you're going to get the exact same result. Okay. Okay. So visually, it looks like this. And so let's say that we have our domain like this. And once again, I'm going to put the optimal point right here. Okay. Okay. And once again, we're going to start in the bottom left corner of the screen. Okay. Where the horizontal axis we'll call it x1, vertical axis will be our second design variable x2. Okay. So we're only going to change one variable at a time. And so, if we're making a change just in x1, that's basically equivalent to moving in the horizontal direction. Okay. Okay. And so in this step right here, we only change x1. All right, and so after we change x1, we're going to make a change in x2. So a change in x2 is going to be a vertical step. Okay. And we're just going to keep repeating this. And so we're going to move like this, move like this, move like this, move like this, move like this. Okay. And then eventually you're going to kind of land on the optimum point where you're not going to see any more improvement on the objective. Okay. All right. And so a much more kind of structured, systematic approach here. Okay. And so for any given step, the direction that we're moving is pretty much known, right? So we know exactly which direction we're going to step in. The thing that's actually going to be difficult in this algorithm is computing how far we should step. So the step length. So the main challenge because the way we're going to do step length in this is going to be different from random walk. And so in random walk, we kind of assume the same step length and we kind of reduced it over time, but in this case, because the direction is fixed, we want to choose our step length to be such that, it's going to lead to the biggest improvement of the objective function. Okay. And in fact, actually, there are multiple different ways to choose the step length. And so initially, we're going to use kind of it's almost like cheating. And so we're going to have like a kind of a cheating method to choose the step length. But then in the second example that we'll do probably on Thursday, I'll show you kind of a more practical method for choosing that step length. Okay. So let's go ahead and start the algorithm. So this is the coordinate search algorithm. Okay. So first we have step one. So step one is to have a starting point. Okay. So that's always important. Okay. And in fact, for all the algorithms that we're going to go over from here on out, we're going to get at least one starting point each time. Okay. And so just like we did in random walk, we're also going to evaluate the objective function at that initial point. Okay, so we kind of get like a good base. Okay. All right, so step two is to set the search direction. Okay. And so remember the search direction here is going to be just one variable at a time. And so mathematically what this is going to look like is it's going to look like a unit vector in one of the coordinate directions. Okay. And so I'll show you. And so if we have a 2D problem, our search direction is going to either be one or two things. We can either have S1, okay? So S1 is just going to be 1, 0. And S2 will be a direction for the other variable, will be 0, 1. Okay. But of course, you know, if you have more than two directions here, you're going to have to kind of scale this up. Okay. And so, you know, for a and for a 3D case, okay, so this is for 2D. Okay. So for 3D, S1 is going to be 1, 0, 0. S2 here is going to be 0, 1, 0. And S3 is going to be 0, 0, 1. Okay. All right, so you have to choose one of these, okay? And so we're gonna cycle through all of them eventually, but you're gonna choose one at first, okay? Okay, step 3. Step 3 is to compute the step length in this direction that will lead to the biggest improvement of the objective function. So step 3 is kind of the key step in this algorithm. Right. And so, you know, after we take our step, you know, our new location is going to be like this. So we have x vector plus lambda I si, okay? Or that si is going to be the direction, okay? And lambda I, that is our step length, okay? So this lambda I is the step length that we desire. Okay. Right. And so we want to solve for that step length that's going to lead to the biggest improvement of our objective function. Okay. And so one way that we can kind of formulate this problem is that if we evaluate our objective function at this new location, right, it should lead to an improvement. Okay. All right. So I'll take a minute here just to, it's a little bit of a long-winded joke, but when I was a teenager, I used to watch a show on MTV called Pimp My Ride, and so a meme was kind of born from the show because you know, if you're not familiar with the show, basically they would take people's kind of old beat up cars and literally pimp out their ride. So they give it a new paint job, they kind of, you know, add some nice features and things like that. But they always try to make it, like, you know, personalized to the person that owns the car, right? And so, you know, let's say a person is very into gambling or something like that, right? And so they put like something ridiculous, like they put like a roulette table in the back seat of their car, right? And so kind of the meme that kind of came out from this, like, oh, we heard you like gambling, so we put a roulette table in your car. And it's never practical. It always looks ridiculous, but it's always entertaining. And so this is kind of the same thing. And so, you know, for people that are fans of optimization, we put an optimization problem inside your optimization problem, because one way that we can compute the step length is we can actually treat this as another optimization problem. Okay. And so to find the optimal step length in this case, we can minimize this result here. Okay. But instead of minimizing over x, so normally whenever we're running an optimization, we're minimizing over our design variables x. Okay. In this case, we're not doing that. And so in this case, we're actually minimizing over just one variable. We're just minimizing over one variable, which is the step length. Okay. Okay. The good news here is that, you know, this kind of internal optimization problem is not the same dimension as our original problem, because we're only solving for one variable here. So we only want an optimal value for the step length, which is just one. Okay. And so, the good thing is that this internal optimization problem is only 1D, okay? And so what that means is that you can use any of the 1D methods that we've gone through at this point. And so basically anything in homework 4 that we've gone over. And generally speaking, a 1D optimization is a lot cheaper than a multi-dimensional optimization. So this actually doesn't add that much cost. And so it kind of seems like you're running multiple optimizations together. This is usually fairly negligible. So the 1D problem is fairly small. Okay. In fact, for some cases where you have an explicit expression for the objective function, you can actually solve this using classical methods as well. Okay. So that's kind of what I meant. That's kind of what I was alluding to before. So this is kind of cheating a little bit because and so in the first example that we're going to use, we're actually going to use classical methods to find the optimal step length, just because it just ends up just being a lot faster. But in the next example that we'll cover on Thursday, I'll show you how to do this without using classical methods. Okay. Okay. But that's generally how we're going to solve for the optimal step length, right? Because we know the direction. We're only going to be changing one variable, so that's what kind of helps us as well. And so we just want to find out how much we need to change that variable to lead to the best improvement. Okay. So this step right here is probably the most important step for coordinate search, and we're going to use it for our next algorithm as well called pattern search. Okay? So both are kind of similar, and so this step right here, computing the step length, is really really important. Okay. Okay, and so of course this is nice to talk about, but and I'll do an example later to kind of illustrate this part right here. Okay. All right, any questions on this so far? Okay. All right, so let's go to the next step. All right, so once the step length is determined, then you actually just take that step. And so there's no need in this case to actually check to see if it's an improvement, right? Ideally, if you did step 3 properly, then it is going to lead to improvement. So we can just go ahead and take that step. Okay. And so of course, that may be implied by step 3, but when you're doing an algorithm, you have to kind of explicitly mention every single thing that you're going to do, okay? Especially when you're writing computer code. Okay, so once you do step 4, step 5 is to go back to step 2. Okay. Except instead of stepping in that same direction, you're going to change to a different variable. Okay. Okay. And then step 6 here is just to repeat. And so we're just going to repeat this over and over until we reach convergence. All right, so step 6 is basically just keep doing this until we're done. All right, so how do we know when we're done? So how do we know when we can stop this algorithm? Okay. So the algorithm has converged when let's say that we're in step 3 of this algorithm and we're computing the step length, right? If the step length that we compute is 0 or almost 0, that basically tells us that we can't, if we take a step in this direction, we shouldn't step any further because that's not going to lead to improvement. Okay? So algorithm has converged when step length step 3 is almost 0. Okay. I say almost 0 because because of numerics, it's hard to get things to be exactly 0. But if it's something that's very, very close to 0, then we say it's converged. Okay. And so typically what we usually do is we define some variable here. And so this variable here, we'll call this the convergence threshold. Usually we pick some kind of very, very small number for this. So let's say it's 0.0001. Okay. And so basically we're gonna check. So if our step length is less than epsilon, our convergence threshold, okay, then we are done. Converged. Okay. All right, and so you're going to see that in the code as well. Okay, so we need to check for convergence. Okay. Any questions on this before we jump into an example? Okay. All right, so let's do an example. So actually, this example is the same example that we did before, except we're going to solve it using coordinate search. Okay. All right, so in this example, we're going to minimize. Okay. This function x1, x2. Okay, so it's going to be x1 minus x2 plus 2x1 squared plus 2x1, x2 plus x2 squared. Okay. And so what we want to do is we want to use coordinate search. Okay. And we're going to start from a point of 0, 0. Okay. And so using coordinate search, we're only going to change one variable at a time. So in one step, we're going to change just x1. We're going to find the optimal change in x1 to lead to the most improvement. And the next step, we're going to change x2 and so on and so on. Okay. So before we jump into the code, we have to kind of come up with a strategy for determining the optimal step length. Okay. And for this particular problem, we're gonna cheat a little bit. We're gonna use classical methods to determine expressions for the optimal step length. Okay. All right, so we're gonna need two expressions because we're gonna need an optimal step length for x1 and for x2. Okay. Because remember, we're only changing one of them at a time. So when we're changing x1, that's going to have its own optimal step length, and when we're changing x2, that's going to have its own optimal step length as well. Okay. All right, so let's look at the x1 first. Okay. Okay, and so if we were to apply a change in x1, it would look something like this. So we have x1 plus lambda 1, comma x2, okay? And so basically we plug in x1 plus lambda 1 everywhere we see x1. Okay? So this is going to be x1 plus lambda 1 minus x2 plus 2 x1 plus lambda 1 squared plus 2 x1 plus lambda 1 times x2 plus x2 squared. Okay. Okay. So all I've done so far is I just took our original objective function, and then everywhere I see x1, I plugged in x1 plus lambda 1. Okay. Okay. And so using the classical methods, if we want to find the maximum or the minimum of this relative to lambda 1, let's take the derivative of this function, okay? But we're going to take a derivative not with respect to x1, but lambda 1. Okay? So df d lambda. Okay, so let's go ahead and do that. And so we take derivatives here. Just for the sake of time, I'm going to go a little bit fast, okay? And so remember, if the expression doesn't have lambda 1, its derivative is just going to be 0, okay? So first term we have here is a 1, because that's the derivative of just lambda 1 by itself, okay? Then we have a little bit of chain rule, and so we have this term right here, so it's going to be 4 times x1 plus lambda 1. So that comes from this term right here, okay? So the x1, x2 terms by themselves, because they don't involve lambda 1, when we take the derivative, we end up with 0, okay? Next, we have a plus 2 x2. Okay? So that comes from this term right here, right? And so if we distribute that out, we have a 2 x1, x2. So that just goes away when we take derivative with respect to lambda 1. And we have a 2 lambda 1 x2. And so that's going to be just 2 x2. Okay? And then we have the derivative of the last term, x2 squared. That does not involve lambda 2 or lambda 1, excuse me. And so that just goes to 0. Okay, and so we set this whole thing equal to 0. And so if we solve for lambda 1, and so lambda 1 is equal to minus 1/4 times 1 plus x2, excuse me, 1 plus 2x2 minus x1. Okay, and so when we're making a change in x1, this is the amount that we should change it by. Okay. Okay. So before we compute for x2, let's check and make sure that this is a minimum, right? And so let's take another derivative here. And so we take another derivative of this expression with respect to lambda 1. Okay. What we get is 4. The internet was actually pretty good today, except for now in this case. But because our second derivative here is a positive number, you know that this is a minimum, and so that is good. Okay. Okay, so just really quickly, let me go ahead and do the calculations for x2. Okay. I'm assuming the internet's going to catch up eventually.
Professor, for when we're calculating x2, are we doing do we label lambda 2 as well?
Yeah. So when we're changing x2, we're going to call that lambda 2. Yeah. It's on the iPad here, it's just the internet's kind of catching up. In retrospect, maybe choosing another Greek letter than lambda would have been good, because lambda and x are kind of similar if you have sloppy writing like me. There we go, all caught up. Okay, so that's the expression that we got when we plug in x2 plus lambda 2. I know we're out of time, so let me just go ahead and do this really quick. Okay, and so just like above, we're going to take the derivative with respect to lambda 2 in this case. Okay, and so we get from here is a -1 plus 2x1 plus 2x2 plus lambda 2. Okay, we set it equal to 0. We once again are going to solve for lambda 2. And what we get is lambda 2 is equal to 1/2 times 1 minus 2x1 minus x2. And then if you take the second derivative of this expression with respect to lambda 2, then you're going to see that this is indeed also a minimum. Okay. Okay, and so on Thursday when we come back, we're going to start with the example code for coordinate search, and so that's going to be example 3, and so we'll take a look at that, and then we'll move on to pattern search. Okay. All right. Any final questions on this before we wrap it up for today? Okay. All right. So that's all we have time for. So thank you guys for coming today. And so definitely take a look at homework 5. You should be able to do the second problem already. And if you want to look ahead a little bit at the codes for example 3 and example 4, then you can try problem 3 as well. Okay. All right. So thank you guys for coming. I hope you guys enjoy the rest of your day, and I will see you all on Thursday. Zoom people, any final questions before I close it up? Okay. All right. I'll see you Thursday.